Hey guys, this is Alex for Physics 2211, lab number 10, Choose Your Own Adventure. In this lab, we'll be looking at an elastic collision that occurs between two blocks. And our goal is to calculate the final velocity, final position, using the momentum principle with these blocks. And our result was that the physics principles applied to this motion, and Python is very useful in predicting these results. So now we're going to take a look here at Tracker, and we're going to watch as I hit the bigger mass into the smaller mass, the big block into the small block. This bigger block that I started with had an initial velocity and was 3 times the mass of the smaller block. And using our calibration stick and origin, we got our position versus time data for both of the blocks. I did a two mass system because the masses are different, obviously. So then once I had that data, I went here over to Vital and I made our Python shell. Basically, most of the same stuff, initializing our box, our two boxes, creating trails behind them, identifying the system properties. The mass of the first box was 0.3189, 3 times that of the second. And then here we come down to our initial conditions, where ball A has an initial velocity of 2.6797 meters per second. And I got that number from the slope of this graph right here. This graph, mass of a position versus time, represents obviously position versus time, and the slope of this graph represents velocity. So what I did was I took a linear regression from about 0.2 seconds, because that's about when the interaction between the two blocks occurs, and I estimated the slope of that line to be my object's velocity. And then I had our initial positions given by the initial time x, y positions. So then we come down here into this loop, and we calculate our initial object momentum for object A, object B, and the total initial momentum. And then right here you'll see time is less than 0.167 seconds. That's saying that if the time is before the interaction, right, ball A will have some sort of initial velocity. However, ball B will be 0 because the second box is stationary, it is not moving. Basically this means that before the interaction occurs, object A will have some velocity and object B will at rest. However, if that's not the case, we're going to use the momentum principle to calculate the final velocity of object B, and we'll assume that object A comes to a complete stop, therefore having 0 velocity. So we do that by saying that the final momentum of the system is equal to the initial momentum, or the final momentum of object A plus the final momentum of object B, and we'll calculate that by saying that the final momentum of object B equals the initial momentum total minus the final momentum of object A, and that is the momentum principle. And then we'll go ahead and run this for you, and you'll pay attention to the blocks. You'll see that this block came with an initial velocity and completely stopped once it hit the smaller block, and the smaller block quickly accelerated to have some final velocity. And you'll notice that the smaller block went very far and very fast. That's because this block was heavier and it transferred more momentum, so this had to gain more speed. However, this showed that it was a completely elastic collision, and this shows that the kinetic energy final is equal to the kinetic energy initial, and there is no delta E internal. And we'll talk about that a little bit later. So now we're going to go over here to Excel, and we'll look at some positions as a function of time graphs. Okay, so the first thing I want to point out is this green line, box 1 from Tracker. So this green line, position versus time, obviously, shows that the object had some initial velocity. It was pretty constant. However, at 0.2 seconds when the interaction occurred, it didn't go to 0. It still had some initial velocity, it still had some velocity. It didn't go to 0. Box 2, you'll see, was at 0 velocity, was stationary, and then at the time of the impact, it quickly picked up velocity and quickly, continued to accelerate out. However, we see something a little bit different with Python. When we look at Python, we see that box 1, which is this blue line here, had some constant initial velocity, very constant, right? And the second that that interaction occurred, the velocity went to 0. And that's because it transferred all of its momentum to this red line, or the second box. So this second line, this red line here, had an initial velocity of 0, right? So then when it was then hit at about 0.2 seconds, it quickly accelerated to have some final velocity. You'll notice that's a very, very fast final velocity. So it's faster than we are normally predicting, and because of that, it's going farther. You'll see that its total position is a lot higher than we estimated with Python, or with Tracker rather. And that's because in Python we're assuming that this is a perfectly elastic collision, meaning that delta E internal is 0. However, there's still frictional forces on the ground. There's other forces that we can't quite account for in this scenario. The fact that object A is still moving slowly, still slowing down as it hits object B is not accounted for in Python. Python just assumes that object A, the second that it comes into contact with object B, it stops. Okay, but however, regardless of that, momentum is still conserved, and this therefore proves that it was an elastic collision. So we see that object A, or the first box, is coming along with some velocity, or some momentum, 0.854 kilogram meters per second, right? And then the second that it hits the other block, box 2, which is stationary for that entire time, right? The second that it hits, it transfers all of its momentum. So you'll see that this had an initial velocity, or an initial momentum, and the second that it hit this block, it quickly went to 0, and vice versa. Box 2 picked up that momentum and had the exact same value, showing that, again, momentum was conserved. However, this is a completely ideal situation. And that makes sense because if we were to plot this, I know this is a very simple graph, but it does say a lot. The fact that the blue line represents the total initial momentum, the red line represents the total final momentum, and they both have the same values. They're both at the same height, right? They both have the same total momentum. So therefore, momentum is conserved in this example. So there you go, guys. That is my Choose Your Own Adventure lab. I've always liked momentum. I'm a real big fan of Newton. So there you go. Take care, y'all.